The plot XY line, plot XY comma line width comma 6, that's just telling it to make the line width 6. You don't really need the line width, otherwise it defaults to, I think, like 2. But and you can also add an extra like you can add a color for the line as well. If you make another comma and type in RGBW for white, and I'll go over that when we get to the CFD part, but that's just something you need to know. And grid on turns on the grid so you can look at it in so the graph creates grids so it's easier to analyze the data. Okay, yeah, this would be the output. This would be the code that you saw on the last slide. This is what it would output. If, as you can notice, the line is really thick, which is why you usually use 2 or 3. But if you like this, then that's good. And this is just a projectile motion. It's a projectile fired at height 2 meters, and the landing point is there. That's something similar. That's another function that's plotting the same kind of trajectory at height. Oh yeah, another thing to note about functions is that you cannot call them within the same script. You need to create another script and call upon the function there with its own unique inputs, and then it'll produce a graph based on those inputs. So the graph that you saw before, that was with specific input, height equals 2 or something. And like I said, if you call upon angle 30, this angle 30 velocity, that's 100 meters per second, and height 50, that's the output MATLAB is going to generate for you. Now, we're not really going to cover sine waves or plotting like those kinds of functions, but it is good to know, good to match the code to an output. So for example, and wait, it's easier to understand the syntax that way. For example, number 1, you can probably infer that that connects to B because it's a bar graph with values 10, 25, 5, 15. And the heights of the bars kind of closely mirror that. So 1 would fit to B. Number 2, the keyword quadratic is kind of important there because there's only one quadratic equation, and that's C. A looks like a sine wave. And the fact that x is in increments of 0.5 from 0 to 10, meaning that there's 20 dots. And on the rightmost graph, C, it's like kind of dotted. Then you can match to C. And then since there's nothing left except A for 3, you would generally say 3 fits to A. But you can also tell because y as a function of x is trigonometric and the function looks periodic, so it would be A for 3. Next. All right, so you're going to be given a launch angle, time of flight, and the velocity, the initial velocity. And using MATLAB, you need to try to find the initial height. Try not to use this as a graphing calculator. Try to find how the height evolves over time, if that makes sense. So I would like you guys to graph it. Okay. So guys, take this opportunity to copy this, use it as a template, and try to understand what the code is and where it comes from. Okay, I hope you guys can see my screen. Basically, I'm gonna use a different function for this. Or let's just do the same one. So for this one, I'm going to use the final velocity example on the kinematic slides. This is going to show how the velocity is evolving over time. but this is more about the syntax, not. Uh, so right now, what I just did is I created a function called final velocity, which takes an input of initial velocity and the final time to find how it's going to evolve over time. And let's just add acceleration as well in there. Or it's easier to just put A. All right. Oh yeah, it's always good practice to indent, by the way. So just don't let the Copilot generate random stuff for you. Uh, so the equation was VF equals V0 times T or dot times, remember? Otherwise, it does something called matrix multiplication. Plus okay. And then before that, though, we need to define what time is. And since time isn't a singular value, we need to define time over a line space of let's say 100 points. That's usually the norm. And then I'm just gonna have to plot it. So then we end the function off. Right. So this will basically just plot it. But first you need to save it. Not bad. Save it in another save it wherever, and then go into another file, call upon your plot, final velocity, plug in your inputs, 10, say ends at 10, and then click editor, click run. Oh wait, shoot. These are my old plots. Sorry about that. And yeah, see, it'll plot how the velocity has changed over time. So you can use this as a template, or you can use the one on the slides as a template, but that's basically how you do it. Okay, so for this one, oh, X is the range, the range. Uh, basically like where it lands. So if you refer to the kinematics equations, the X distance is just velocity times time because there are no forces acting on the in the X direction. So first you need to convert the angle to degrees. That's the first step. Then you need to convert it to the horizontal component. Then you need to initialize your time variable and create something for your range or describe how range changes with time. And then you just plot the graph. And then you should get a graph kind of like this. Let me share my screen. Or wait, hold on. I'll create the graph first and then I'll share it. Ooh. Give me one sec. Or I guess it's better to just show you guys again how I would call it. So I have the function pulled up over here. Again, I'm just gonna go into my other editor or other script. I'm gonna call in plot proj3. The angle was 30 degrees again. The time it was in the air was 0.82 seconds, I think. And then the initial velocity was 7.43. And I'll just run it. Oh, and then I need to share another file for this because the output is on a different thing. Um, yeah, this is basically the graph you get. So here, click on this, you'll find out that the y distance is 5.27 meters. So it lands 5.227 meters away. And that's the answer to the question. And it's linear because velocity is not changing in the x. There's no acceleration. And this is just how it changes over time. So yeah. Right. Finally, it's time to do the something that most of you probably will need in terms of ACEF, and that's with data analysis. Now that you've gotten comfortable with the syntax, it's time to transition into data analysis. So I'm going to send a couple links in the chat. Use those to download these 3 data sets that we're going to have you analyze with MATLAB. So give me a sec. I'll find that real quick. So first to import the data, go into the Home tab and click that Import Data button. The files should be in the form of CSVs after you download them onto your computer. And I made it so that the names of the files are already like UX, UZ, and UI. So if you see those, just click on them and open all 3 of them. They should be 4 by 1000 in terms of size. It seems like a lot, but it's because we measured fluid flow in a pipe over 1,000 seconds across 3 surfaces. And that's what the data is. And wait, let me just show you how to do this while sharing my screen. It's probably best. Okay, so I'm going to open a new script again, because that's where I'm going to do my data analysis. This one doesn't have to be a function because I'm not going to keep using it. There's no repetition. I'm just going to go into the Home tab, going to click on Import Data, and I'm just going to find the file that I want to import in my library. And that is pretty much all you need to do in terms of that. Yeah, so for example, I'll just import the UZ. And then it'll open up another window. You just don't even look at that. Just click import selection on the top right, and it'll import the variable for you, or the data. So we'll give you a few minutes to figure that out. If you have any questions, just type them in the chat.